Hello friends, today we will solve the GATE 2025 Electronics and Communication Electromagnetics problems. Okay, so these are three problems. First one is like a square metal sheet is given 4 by 4 mm, 4 mm by 4 mm. It is placed in xy plane and surface charge density is 4 times mod y. So we need to find the total charge on the sheet. So surface charge density is a function of mod y. Okay, so as y increases in both the direction, the surface charge density will increase and it is independent of x. So it will be like lesser here and more here. Similarly, it will be lesser here and more on this side. So one way is to like since it is symmetric, so we can find the surface charge density on 1/4 of the part and then multiply it by 4. Okay, and q net is equal to surface integral of this surface charge density times dx dy, because the sheet is placed in xy plane. And so this is like from 0 to 2, x will vary from 0 to 2, y will also vary from 0 to 2, and between 0 to 2 y is positive, so we can put mod y is equal to y, so y dy, you can take 4 out, so 4 times integration from x is equal to 0 to 2 dx, and then y from 0 to 2 y dy. We are able to separate these integrals because limit is constant and they are independent of each other. Okay, so this part is like x from 0 to 2, which is 2, and this part is like y square by 2 from 0 to 2, so which is basically 1 by 2 times 4 minus 0, so this is 2, so this is like 2 into 2 into 4, so it is 16, 16, 16, 16, 16, so it is 64 microcoulomb per meter square. Or what you can do is like you can directly use entire integration, so q total is like from minus 2 to 2 and y is equal to minus 2 to 2 and then 4 times mod y dx dy. So this part is like dx from x is equal to minus 2 to 2 and this 4 is taken outside, and then mod y is an even function. Okay, just like mod x is an even function, mod y will be an even function, so we can put it as y from 0 to 2, 2 times this 0 to 2 y dy, so this is again like y square by 2. Okay, so which is half times 4 minus 0, so 2, so this part is 2, this 2 will be there, and then this thing is 4, this thing is 4, again you multiply, you get 64 microcoulomb per meter square. Okay, so this was pretty easy question on electrostatics. Another question, this I also discussed in DC part, but let's study it, discuss it again here. So this is from this normal current density formula, Ohm's law, J is equal to sigma E. So its electric field is applied along the length of a copper wire of circular cross section of diameter 1 mm. So when copper conductivity is given, so the current flowing through the wire is, okay, so current we need to find out. So current density is sigma times E, so current density is current per unit area. Okay, conductivity is given, electric field is given, and area will be equal to pi r square, cross sectional area of the wire. Okay, because it will be circular wire, so we need to find this area. So this cross sectional area will be pi times r square. 1 mm is the diameter, so 0.5 mm means 10 raised to power minus 3 and then square, so we just need to multiply this. So current will be 22/7 into half into 10 raised to power minus 3 is basically 1/1000, then again half into 1/1000 into 5.8 into 10 raised to power 7, so this is like 58 upon 10 10 raised to power 7, and then this part is 0.01 upon, so this take 100, and then these 7 zeros will be cut by this part, so this is 1/100, and so 22/7 into 1 by 4 into 58 into divided by 100 is 0.46, so this is the answer, 0.46 amperes. Okay. Third question is from transmission line. A 50 ohm transmission line is terminated with load ZL of 50 minus J25. Okay, and so load is given ZL, and then if the average power incident is 10 milliwatt, then the average power delivered to the load will be, okay, so we need to find average power delivered to the load. So this is the transmission line with Z node characteristic impedance as 50 ohm. Okay, and this is ZL. So power incident is 10 milliwatt, and this is the load. Okay, it's a complex load. So we need to find power delivered to load. So power delivered to the load will be power incident minus power reflected. So incident power is P incident, and power reflected will be equal to P incident minus lambda L square. So when we take P incident common, so it will be P incident 1 minus lambda square. Okay. So P incident is 10 milliwatt, and 1 minus, we need to find the reflection coefficient at load, which is ZL minus Z naught, ZL plus Z naught. So ZL value is given here, 50 minus J75, and then minus Z naught, ZL plus Z naught, which is minus J75, 100 plus J75, which is basically, if we take divide everything by 25, then minus J3, 4 plus J3. Okay, so what will be mod ZL? So mod ZL will be basically 3 upon 5, because it will be under root 3 square divided by under root 16 plus 9, so this will be under root 25 5. Okay, so mod ZL is 3 by 5, so 1 minus mod ZL is 1 minus 9 upon 25, so this will be 10 milliwatt, and then this will be 16 upon 25, so this will be 32 upon 5, so 6.4 milliwatt. Okay, so this was again easy question. Similar concept is also used in like normal incidents in plane waves, like incident power is from medium 1 is like pi, and reflected is power of the wave is pr, then p transmitted is pi 1 minus this lambda square. Again this reflection coefficient symbol, which is again neta 2 minus neta 1, neta 2 plus 1. Okay, so which is intrinsic impedance of medium 1 and 2. So similar concept is also used in plane wave also. So reflected power is reflection coefficient square times the incident power. Last question is on Faraday's law. Okay, so it is saying that two resistors are connected in a circular loop of area 5 meter square as shown in the figure. The loop circuit is placed in xy plane. So it is placed in xy plane. A time varying magnetic field with flux density Bt is equal to 0.5 t Tesla is applied along the positive z direction. So magnitude of current I in the loop is, okay, so the loop is placed in xy plane, and the magnetic field is, so perpendicular will be z, and to this plane is z, and the magnetic field is also passing through z. Okay, so let's see how we'll proceed it. So let's study some basics of Faraday's law first. Okay, so Faraday's law of EMI, electromagnetic induction, basically describes how a changing magnetic field induces an electromotive force or voltage in a closed circuit or any closed conducting loop. Okay, so मैग्नेटिक फील्ड अगर चेंज होगा तो उससे क्या होगा, क्लोज सर्किट में एक ईएमएफ या वोल्टेज डेवलप होगा. एंड कैसे होगा, तो दिस लॉ स्टेट दैट इंड्यूस्ड ईएमएफ इज डायरेक्टली प्रोपोर्शनल टू द रेट ऑफ चेंज ऑफ मैग्नेटिक फ्लक्स थ्रू द सर्किट. तो मैग्नेटिक फ्लक्स जो है वो कैसे चेंज हो रहा है टाइम के साथ, दैट विल डिसाइड द इंड्यूस्ड ईएमएफ. ओके, so for example in this question this magnetic flux will be changing. Okay, and this changing magnetic flux through this loop will produce some voltage in this loop. Okay, and the formula of induced EMF is minus d phi b by dt, and where this phi b is basically b dot a, which is ba cos theta. Okay, a is what, it is the area of the circuit through which the magnetic line is passing. Okay, so this area, this area is the loop area, and theta is the angle between the magnetic field line and the normal to the circuit surface. So the direction of magnetic field line and the normal to the circuit surface will be theta. Okay, and this is magnetic flux density, and this is area. So the phi b is basically magnetic flux. Unit of magnetic flux is Weber, and unit of magnetic flux density is Weber per meter square of Tesla. Now the current induced in the circuit, in the closed circuit or closed conducting loop I is equal to the EMF upon the net resistance of the circuit. And if it is magnetic field is non-uniform, like it is varying with respect to space, then we use phi b is equal to b dot da, and theta 2 points is like if the field is perpendicular to the surface like as here, then theta is 0 resulting in magnetic flux, maximum flux, and if the field is parallel to the surface, and theta is 90 resulting in 0 flux. Okay, so here you can see that normal to this is also z direction, and the field is passing in is also varying in z direction, so maximum magnetic flux will pass through it. Okay, so here time varying magnetic flux is 0.5 Tesla. Okay, and area of the circuit is 5 meter square, so 5b, which will be b a cos theta, will be, and theta is 0 because this loop is also placed in xy plane, so magnetic field will also pass in z direction, and normal is also z direction, so theta will be 0, so it will be b, and this is a, so this is 2.5 t 5b. So induced EMF minus will be equal to minus d 5b by dt. This minus is due to Lenz's law, so this is like minus 2.5 volt. Okay, and therefore the current that will flow in the circuit magnitude will be magnitude of EMF divided by R net. So here you can see the R net will be 2 plus 2, both are in series, so it will be 4 volt, and induced EMF is 2.5 volt, so the current flowing through it will be the circuit will be 0.625 ampere. Okay, thank you. So these were only 4 questions of EMFT. Thank you.